Hello everyone. In this video, I'm going to be talking to you about multiple regression models. So when we have regression models that use more than one independent variable to explain or predict a dependent variable, this is called a multiple regression model. So here we find, again, our main form of y being equal to now the y-intercept, so beta naught, plus here the different slopes for different independent variables. So we've got beta 1 all the way up to beta k for x1 to xk independent variables. Plus, of course, that other component here, that is the error term. So y is in fact expressed as two components once again. Here we have the mean level component, mu of y, for a given set of x1 to xk values. And here the mean level here relates y to the independent variables, okay, x1 to xk. And then here on the other hand, here we have the error term, which is what describes the effect on y, the dependent variable that is, of all factors that are not included in the x1 to xk independent variables. Very quickly again, beta naught is the y-intercept of the model, and beta 1 or any beta j for that matter from 1 to k is the regression parameter for an independent variable, say in this case x1, and it measures the change in the mean value of y that's associated with a unit increase in, say, x1. So that would also apply to, say, beta k. In the case of beta k, that is a measure, it is a regression parameter that measures the change in the average value of y for a unit increase in x of k. Okay. Now, when we use the least squares point estimates of the regression parameters, well, what we get here are the point estimate for the mean value of y, otherwise known as mu of y, for a given set of values x1 to xk. And so it takes on this form right here. Y hat is equal to b naught plus b1 x of 1 plus all the way up to bk times x of k. So that is a point estimate for mean value of y. When we use, of course, the least squares method to come up with these point estimates for regression parameters. Okay. So in other words, we are saying here that y hat is a point estimate for mu of y for a given set of x1 to xk values. Okay. Now what's interesting also here is, well, let's not forget, because it has been covered for simple linear regression, but let's review that again. We say that with the least squares point estimates, we also can obtain a point prediction for an individual value of y, for given values of x1 to xk. And so that takes on the form right here. Y hat is equal to b naught plus b1 times x1 plus all the way up to bk times xk. Okay? Now, why is it that the two have the same form? The point estimate has the same form as the point prediction? Well, the reason is that if we follow here the four model assumptions on the error terms, so let me just scroll down here and let's quickly review what these four model assumptions are. This was seen in simple linear regression. So here we are. It is again the same assumptions that we have seen. It is now extended to multiple regression. So the error terms are assumed to have a mean value of 0, constant variance across all different values of x for each independent variable over here, and the normality assumption of the error terms, and that is that the errors are normally distributed for each combination of x values, and the independent assumption as well, and that is that the error terms are independent of each other across all x values. Okay, so much the same as what we've seen before. So when these model assumptions hold, then um, we can affirm here that y hat serves as a point estimate for the mean value of y, and it also serves as a point prediction for an individual value of y. And let me explain to you a little bit more on the point prediction why that is the case. So over here, we have that the error term, will sometimes be as a result of the y hat value being greater than, say, the observed value of y for a given set of x1 to xk values, right? In which case here, when we look at the formula for the error term, that will yield over here an error term that is negative, right? And in other instances, the y hat will actually be smaller than the observed y value, in which case here we will have an error term that is positive. And so we say that if the four model assumptions hold on the error terms, then we can say that 50% of the time the error terms will be negative, and 50% of the time these error terms will be positive. And so by taking the predicted value of the error component in this multiple regression model, if we were to take the predicted value of the error term, well, that would give us as an end result 0, a value of 0. And hence we say that the point prediction for an individual value of y is set to be of this form right here. Okay. Okay, so then we move on to look at the example that we had from simple linear regression. So we were looking at annual revenues. We took a random sample of 10 restaurants, and we got these annual revenues over here. And we, sorry, here they are. Yes, and so for that we got an x value here. Here call it x1 because now we are looking at multiple independent variables. In fact, here we are looking at two independent variables. X1 is the population size in thousands of units where the randomly selected restaurant lies, where that restaurant actually is found. So we have the population areas over here. And so now we are also interested in knowing how does a business rating in that area, so a business rating here of how like the businesses are doing in general, and perhaps a shopping area as well in that given area, does on a scale of 1 to 10. So we've got that added independent variable x2 business rating, and we'd like to know how that also affects the yearly revenues for a restaurant, right? So, okay. So if we obtain here the point estimates for the regression parameters beta 1 and beta 2 as well as beta naught, in fact we get here our point estimates b naught is here in this case 125. 0.289. B1 is another point estimate. This is, of course, always obtained by method of least squares, right? So we get our B1 point estimate for beta 1, and we get our B2 estimate for beta 2. And so let me just tell you here, by the way, that these point estimates are no longer obtained. You can no longer compute them manually. You'd have to use your matrix algebra to get these values, which is not in the scope of this lecture, this lesson, right? So we leave it to the statistical packages here, be it Excel or Minitab or any other statistical package that you're using to compute these point estimates for you. So you don't need to worry about that. Here, you must rely on your statistical package to to come up with these point estimates right here. Okay, so when we get our point estimates, as a result, we are able to get our point predictions, if you want. So here we are. These are the point predictions. So we're getting 10 point predictions, one for each observation that we have. So for instance, let me just zoom in a little bit here. For the first restaurant here, if I am to use x1 equals 20.8 and x2 equals 3, then my predicted value for y will be 489.07. Of course, this is in thousands for annual revenue. And so I'm comparing that to the predicted, to the observed value of 527.1. As a result, I get a residual here. Y minus y hat gives me here a positive residual, and that is because my predicted value is smaller than my observed value. So if I do this across all 10 observations, I will get a set of residuals over here. Some will be positive, some will be negative. What I'm interested in here is obtaining my sum of squared residuals. And so the sum of squared residuals is obtained across all 10 observations and all 10 predicted values. And this value that I get here of 9,420.8 should be, in fact, the minimum possible value that I can get for sum of squared residuals. If I have used my least squares method to come up with my point estimates for my regression parameters, so these values right here, these are my point estimates. Well, these point estimates should guarantee that the sum of squared residuals is at a minimum, okay? So any other way of estimating the regression parameters, in other words, would not give me such a minimum value as this one right here. Okay. Okay, so so then moving on from that SSE measure that we get, we say that the mean squared residuals over here, so that is by taking the SSE and dividing it by n minus k minus 1. That gives me the mean squared residuals or mean squared error measure. Well, this is equivalent to the sample variance of the model. Okay, call it S squared. And it is intended to serve as a point estimate for sigma squared, the true population variance, which I do not have here, so I'm using my sample, right? Now let me just discuss very quickly what goes into determining MSE. So we've got here the sum of squared residuals divided by n here being my sample size, so I've got 10 observations in my sample, minus k. K here is the number of independent variables that I'm using in my multiple regression. I've got here 2 independent variables, minus 1. Okay, minus 1, because let's not forget that I am also using an intercept, an estimated intercept over here, B naught, right? So minus 1. Hence, I've got in my denominator over here, 10 minus 2 minus 1 gives me 7. And hence, I can get my MSE, my sample variance for the model. Further, I can now get my standard error of the model. Standard error is simply taking the square root of S squared to give me S, which means, in fact, square root of MSE. Okay, here we are. So that will serve as my standard error of the model. Very quickly again, when we talk about the different variations that are contained in the observed y values. Well, we also have here another source of variation, and that is SSR, otherwise known as the explained variation in y. And so yes, by the way, over here, let me just quickly remind you that SSE accounts for the unexplained variation in y. Okay, so we've got the unexplained variation plus the explained variation. Explained variation is everything that relates to the regression model. Okay, so here we look at how each estimated y value compares to a benchmark model y bar, very basic average y values, right? And we take the sum of the squared differences over here to get, in the end, this SSR value, sum of squared regression residuals, if you want. Okay, and we divide that by k in order to obtain our mean squared regression residuals. K, let's not forget over here, is the number of independent variables used in the multiple regression. In this case, we've got 2. And finally, we have our total variation in y is accounted for by taking the sum of the sum of squared regression residuals, or explained variation, plus the sum of squared residuals, or the unexplained variation. So total variation is equal to explained variation plus unexplained variation. Okay? So if I have all this information, well, now the next step is to determine how effective is my multiple regression in explaining or predicting the y values, right? So one way to get that information is to look at the multiple coefficient of determination. So in simple regression, we looked at a lowercase r squared, which we said varied between 0 and 1, and that was called the coefficient of determination. Now in multiple regression, we call this an uppercase R squared, and you can call it multiple coefficient of determination. It follows the same formula as for simple coefficient of determination, and that is that it is the proportion of the total variation in the n observed y values that can be explained by all k independent x variables, and hence it has this form SSR divided by SST, or in other words, how much of the k independent variables accounts for the total variation in the n observed y values, right? That is what it is measuring. So it is a proportion of explained variation relative to the total variation. And so here again, we get a value that will be between 0 and 1. Okay? Now, of course, if we can get the multiple coefficient of determination r squared, then we can also get the multiple correlation coefficient, which will simply be the square root of r squared. Okay? And so now one thing to note is that even if now all k independent variables, so it can happen sometimes that all k independent variables are not related, or maybe somewhat related to y, the dependent variable y, there is a thing here, and that is that by default the r squared over here, this r squared, will tend to overestimate the importance of the k independent variables. So that is just the nature of multiple regression. It is one of these things with multiple regression. The more independent variables that you put in there, no matter how much or how little these independent variables are related to your dependent variable y, by default, the r squared will overestimate the relationship between y and your independent variables. And so to correct for this overestimation, we introduce here another measure, and that is the adjusted coefficient of determination. The adjusted coefficient of determination here, you can see, is in fact taking your coefficient of determination r squared and subtracting from it this fraction of k over n minus 1 times this coefficient right here, n minus 1 over n minus k minus 1. Okay, so that will somewhat reduce the r squared. And so this adjusted coefficient of determination is represented by this notation right here, r squared with a bar on the r. Sometimes you'll also see r squared subscript adj, adj representing adjusted. Okay, and so, well, what happens here, sometimes it doesn't happen often, but it can happen that sometimes your r squared coefficient of determination will be less than this fraction of k over n minus 1. Well, when that happens is you'll get a negative adjusted coefficient of determination. But statistical packages, usually what they'll do in these cases is simply put the adjusted r squared to be equal to 0. Okay, so these cases can happen sometimes, but not often, just so that you're aware. Okay, and so now let's just quickly go look at an Excel output and see how these coefficients look like in an output. So here we have our multiple r. The multiple r is in fact this multiple correlation coefficient. It is your r value right here. Then you've got here your r squared. The r squared is in fact the coefficient of determination right here. That's the SSR over the SST. And then you've got the adjusted r square, which is as a result of subtracting this fraction and then multiplying by this coefficient. And you can see here how the adjusted r square is always less than your r square, right? So it's always less than or equal to, but never greater. It can be perhaps equal to your r square or less than, but never greater than r square. Okay, and then this this value, the standard error that I have in the orange box right here, well, that is in fact your standard error of your model, right? So it's this value right here, S equals the square root of the mean squared error term. Okay, so that is all for now, and I'll continue in a next video to complete chapter 14. Thanks.